Okay, this is for the alien ship in orbit problem. The question reads, an alien ship is in a circular orbit around the Earth, maintaining a 4,500 kilometer altitude above the Earth's surface at a constant speed. Okay, so circular orbit, that means we're talking about circular motion and uniform circular motion because it's at constant speed. So all right. And then we're asked in A, what speed must the ship have to remain in this orbit? You may need to know that the radius of the Earth is 6,380 kilometers and the mass of the Earth is 5.97 times 10 to the 24th kilograms. Okay, so you may need to know. And it's dropping a rather large hint there. Okay, so we know that it's circular orbit. And remember that in uniform circular motion, we want to know what forces are acting on the spaceship to keep it on that circle. Now, because it's in orbit, none of our normal forces can act on it except for gravity. So when we write out our centripetal force equation, which is the net force towards the center of the circle, that is going to be equal, this net force centripetal is going to be equal to the force of gravity on the alien ship. And the one thing here that we need to remember is that the alien ship is nowhere near the Earth's surface, so we need to break out the Newton's universal law of gravitation version. And the two masses here, I don't want to write M1 and M2. I want to write mass of the spaceship, so M, and I want to write mass of the Earth because that's the other mass involved in the gravitational attraction here. Okay. So if we're looking at this, we don't need to know the mass of the spaceship, and that's good because we're not given it. But we want to know what this V is. So let's work that out. We take the square root of both sides. Okay, so if we're looking at this, the one last little issue is that we need to determine what R is, right? What is this? So R is not just 4,500 kilometers because that's from the surface of the Earth to the thing. Remember that this R in the universal law of gravitation is the distance between the centers of mass or the centers of gravity of the two objects. So we're going from the center of the Earth, okay, that's why you're given the radius of the Earth, to wherever the spaceship is. So that's the radius of the Earth plus 4,500 kilometers, which if we add in the radius of the Earth that we're given there is 10,880 kilometers, or converted to our standard units, which we definitely want to do. We add 3 zeros in the end of there and we get meters. So once you plug everything in here, remember G is just a constant, 6.67 times 10 to the negative 11th. And if you plug everything in appropriately, you should get 6,050 meters per second. Okay, so that's our answer to part A. That gives us the speed, so the magnitude of the velocity. Now, you have a B and a C here. So what's B? How long does the ship take to complete an orbit? Okay, so this is something that is simple, but also not something we've encountered except maybe once. So we just need to think about this carefully. We know about velocity, we know about distance. We know that the circumference of a circle is 2 pi r. And so the amount of time that it takes to go around an orbit is going to be the speed we just found, equaling the distance covered over the time it takes, right? So when we put that in there, and remember that this r again is the radius of the orbit, so be this large number of meters divided by time, and we multiply by time, we divide by v, and we get, well, I could put this in scientific notation, I suppose, but we'll just go with it for here. You will get about 11,300 seconds, which is a little over 3 hours, 3.14 hours, I think. Okay. So that's how long it takes in that orbit to go around the Earth, as would any other satellite. Okay, so there's that. And then for part C, we are asked a concept question. So the Earth vanishes, leaving nothing behind. Describe the trajectory of the alien ship after this happens. You may assume that it does not use any propulsion. Okay, well, I mean, eventually this thing would start being affected by other heavenly bodies, things like the sun and the moon and Jupiter and all these other things that are around the solar system. But in the moment, if its velocity is, say, in this direction, as it orbits the Earth and it presses the button and it makes the Earth go away, well, then the force of gravity goes away. So there's no reason for it to stay on the circle, and Newton's first law takes over, and it will travel in that direction, right, in the direction of its velocity until acted upon by an external force. So we can say that relatively succinctly. Newton's first law, and I've already drawn the direction that it goes. And that's because there's no force keeping it on the circle. Okay, good, done. See you for the next one.